Hi, welcome to Science Odyssey. My name is Douglas Fernick. I'm a professor of mathematics at the University of Regina. And today I am going to take you through a short journey up with the beautiful real number pi. So let's start by asking the question, what is pi? Well, everybody knows that pi is 3.14, but it's actually a little bit more than that. It's 3.141592653589799. Oh, I'm tired already. But the key thing is, this goes on forever. There's infinitely many digits. But that doesn't give us very much information about what it really is. And why would we care about a number that has an infinite decimal expansion of this type? So, you really are perfectly justified to ask, what is pi? Why should you care about pi? And does pi have any practical use? And I will try to address these questions in a lecture that I think will take about pi squared minutes. Okay, the most important thing about pi is that it relates circular quantities. So we have here two circles, a big circle of circumference c and a small circle of circumference c prime. The circumference is the distance traveled when one walks along or traverses the outer edge of the circle. Now the big circle, we have a diameter called d, and the small circle has a diameter called d prime. The diameter is the distance traveled when you go from one edge of the circle to the edge of the circle across from it when passing through the center of the circle. And what the classical Greeks noticed in 300 BC is that the ratio of the circumference to the diameter of the big circle is exactly the same as the ratio of the circumference to the diameter of the little circle. In other words, the ratio of the circumference to the diameter is constant, regardless of how large or how small that circle is. This constant is a real number that we denote by the Greek letter pi. So the way we spell pi in English is pi, but we pronounce it as PIE, pi, just as in apple pie, which we can't help but note is also a circular entity. Now, another thing about pi, and maybe people know this more, is that the radius, which is half the diameter of a circle, is involved with pi in determining the area of the circle. So it's this famous formula that says that if you take the radius and square it and multiply it by pi, you get the area A of the circle. Now, if we go to higher dimensions, because a circle is simply in the plane, which is 2 dimensions, if we go to higher dimensions, we get the volume of a sphere is 4 pi r cubed, all divided by 3. In 4 dimensions, which you might not be aware of, but there's a 4-dimensional mathematical world, we also have a formula for the volume of a sphere. And in any arbitrarily high n-dimensional world where n is some finite counting number, we have a volume of a sphere. So pi occurs in all possible dimensions relating volumes of spheres in those dimensions and giving exact formulae. Now, what is the value of pi as a number? Well, Archimedes proved that pi is a number that is somewhere between 223 divided by 71 and 22 over 7. Now, if we looked at the decimal expansions of those numbers that pi is sandwiched between, it gives us a pretty good approximation of pi to 2 decimal places, as being 3.14. So already 2,500 years ago, Archimedes was able to determine that pi to 2 decimal places is 3.14. Now, in 1761, Lambert showed that pi is an irrational number. Now, what a rational number is it's a number that can't be expressed as a ratio of whole numbers, such as 22 over 7 or 223 over 71. So that means that the decimal expansion of pi requires infinitely many non-repeated digits. So in that regard, pi is very difficult, well, impossible. It's impossible to determine all of the digits of pi. And so while this expression for pi is very close, it's a very good approximation to pi itself, there remain infinitely many missing digits. Okay, so now let's look at some other values of pi through history. So if we go back to 2000 BCE, we had pi. The Babylonians had it as 3.125. The Egyptians had it as 3.16045. And as we go through in time, getting closer and closer to the modern era, we get pi to more and more places of accuracy, like 527 places of accuracy in 1874. But then we have this strange anomaly in 1897 where the state of Indiana declared pi to be 3.2. That doesn't seem like progress. It seems like a step backward. Fortunately, the state of Indiana has corrected that since that time. Now let's look at some interesting formulae involving pi. Now, the first one we're going to look at involves the most important numbers in all of mathematics. And these are the number 1, the number 0, the number -1, and the square root of -1, and pi, of course, and e, which is known as the base of the natural logarithm. And they are related by the following marvelous formula. E raised to the power pi times the square root of -1 plus 1 is equal to 0. And what mathematicians like about this formula is hidden inside it is the Pythagorean Theorem as it arises in trigonometry. So the relation of inscribed triangles within circles. So this is a very beautiful equation that mathematicians feel that ought to be put on t-shirts. Okay, so what are the counting numbers? Well, there's 1, 2, 3, 4, 5, 6. Their reciprocals are 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so forth. 1 over 6. There's infinitely many of those. And now we would like to square each of those reciprocals and add them up. And in doing so, we'll get some number, and it remarkably relates to pi. That number is pi squared, all divided by 6. And in this derivation, the Pythagorean theorem, which we know from elementary geometry, that the hypotenuse squared is the sum of the squares of the other two sides, has a role. It's a hidden role. It's like a version of the Pythagorean theorem in infinitely many dimensions. And here's another formula. I'm just going to show it to you without explaining to it, but it allows us to do fast computations of pi. With each time we add a sum here, this is an infinite sum, we produce 14 additional digits of pi. And just to wrap up this section, there's a couple of more beautiful mathematical formulae involving pi that you might know if you happen to know calculus, or if you don't know calculus, it's interesting to see that this formula at the bottom is related to the fourth power of pi, not unlike the formula we had earlier for the second power of pi. Okay, let's turn to some practical uses for pi. We've needed pi for a long time, and we still do. Early civilizations needed pi to accurately subdivide agricultural land after flooding. Later, pi was required to accurately circumnavigate the seas. But to navigate the seas in a pre-20th century sailing vessel, we only needed pi to 6 decimal places. Now, today, we need pi to compute the circumference of the Milky Way galaxy to with an error that is less than the size of a proton. And here, we can get away with just 40 decimal places of pi to do that remarkable calculation. And finally, we also use pi to determine whether computer processors actually work. I hope you have enjoyed this small introduction to the beauty of pi, and thank you for journeying with pi and me during your science odyssey.